Welcome in to session 4. This is a huge topic, guys. We've been wanting to do a session like this for a long time. It just has never quite fit in to the curriculum we've developed until now. Today we cover embeddings, and we've tried to do our best to contextualize this. As you'll see, it really is all about context when it comes to embeddings, well, and building, shipping, and sharing production LLM applications in general, which is exactly what we are on a mission to do with you guys and our community at AI Makerspace. What has been happening around the community this week? Quick shout outs. And we're going to start focusing this in more on what you guys are doing in the cohort. Akash really crushed the community session. Looks like it was kind of a banger. So shout out to everybody that attended there. We had a great transformation of the week that we highlighted. This was really cool to hear Schwanello, although he was a very seasoned consultant. Sort of he had what he needed in terms of confidence and speaking the language to be able to really take to the next level with a corporate investment bank and really be seen now as the thought leader for those large teams with inside that corporate bank. So shout out to Schwanello for sharing his story. Also, I want to focus in on just a couple things that I saw this week. DK, my first fine tuning, loved this. Okay. Love to see this in the Discord. And then, you guys in the cohort, Sahar, shout out to Sahar, really starting to get after it. I love to see this, Sahar, I really do. Keep it up. Keep showing that leadership in the Discord and on LinkedIn. But also, we saw 8Spark and Nalay really start crushing it. Nalay also, he seems to be just shipping and sharing everywhere like a legend. Also on LinkedIn, and shout out to Jacob sharing as well on LinkedIn. So you'll notice, I'm always checking. Wiz is always checking. We're always checking for what you guys are posting and tagging us in. And if you tag us with stuff you're doing in the cohort, every time we're going to amplify for you. So let us know, and let us help you build, ship, and share. And if you're trying to hear about the other stuff going on in the community outside the cohort, start coming to the sessions on Monday morning. We had a real banger this week. Probably about 15 people showed up live. And we are building, shipping, and sharing this week. Tomorrow on-prem agentic RAG. We'll actually meet Llama Index today in a very weird, interesting way. Maybe it sparks your curiosity to be able to join us tomorrow to see how to do on-prem RAG with Llama Index. We'll also kind of meet RAG today in a very interesting way. If you have anything going on this week, obviously I won't be in my office hours on Thanksgiving, but generally people will be available as you're working on stuff. There's going to be a lot to digest and work on after today. And then this was an Ask Wiz, more context or application for, or use case for flash attention is what this should read. And I think the use case is use it generally, right? And that's about it, right? Like we should be using something like flash attention today versus a naive attention when we're leveraging LLMs to build production LLM applications. Is that right, Wiz?
Yep, use it. That's it. If you're not using flash attention, you should be using a different attention that is equally fast. It's hard to find ones that are as fast, so flash attention, there we go.
Flash attention. Do it in a flash. And then for additional context, please do see our YouTube video on that, because we only have so much time in class to cover many topics, and we'll sort of feel that again today. Okay, we have many trailheads that we'll explore together, but the depths of each of these forests are yours, and the richness of them are things that you're going to have to take into the future with you and try to really get a handle on deeply and truly grok. Okay, so I wanted to point out a quick update we've made to the curriculum. Instead of embeddings and embedding models being different sessions, we've combined them into one so that we could leave a little bit more room in the end to cover properly some of the state-of-the-art techniques that are being leveraged to build SLMs today. Things like merging, distillation. It'll give us a little more time to talk about like mixture of experts architectures. It'll give us a little more time to talk about additional fine-tuning techniques that we won't really learn in the single session on fine-tuning using the classics. So we have a sort of a wide-ranging discussion today on embeddings that should cover everything we need, and hopefully you find much more useful than the alternative. So today, let's meet embeddings. What we want to do is we want to understand one of these more common types of ways to encode positional information, confusingly called rope embeddings, that are leveraged in long context LLMs. This is important to discuss now before we move on from the sort of positional encoding and embedding context on to, more greener pastures, sort of towards the output of the transformer, and then ultimately just leveraging the transformers. Today, we're still kind of inside, and we want to enjoy it there. We have one more session inside. We also want to learn to actually create embedding models ourselves. So we want to talk about encoding and embedding layers. We also want to talk about embedding models and creating simple ones. Simple ones like word-to-vec style ones at first, and then going and looking at more complex ones like the BERT style LLMs used today to create embedding representations. We're going to train a transformer with rope. That's going to be just a quick demo that Wiz does. It's not going to be an assignment, but the assignment is going to be really building word-to-vec, and then we're going to actually fine-tune an off-the-shelf embedding model that is much more sophisticated than a word-to-vec type model, but we can sort of scale our understanding pretty easily by going through this process like this. So we want to kind of demystify embeddings today. Want to go through rope and word-to-vec and the massive text embedding benchmark. This is the way we assess how good embeddings are. Now you can see already I'm sort of dropping a lot of new words and sort of things that you're going to have to really spend some time with. So just do your best to kind of pay attention today, and hopefully the discussions in your breakout rooms will continue to lead you down the path of where you're trying to go. We're going to talk also about sentence transformers, also known as sentence BERT. So we can start to see how some of these things are coming together, and we're going to actually get a little insight into fine-tuning, even though we haven't covered fine-tuning while we're here with embedding models. Okay, so first off, let's just start with a few definitions. We really want to embed the definition of embeddings to you today. So I'm going to start with like a bunch of definitions here. If we look at embed, it's like implant something within something else. Okay, so if we define sort of embedding, we're sort of saying we're going to kind of map into this other representation. We're going to sort of embed into this other representation. So we have a few definitions that we've put together that will hopefully make things clear. The first one is that you're going to hear people say the word embeddings. And when you hear them say embeddings, it's instantly unclear, unless you've been following all of their other words and context, what they mean. If they just say embeddings, they could mean either an embedding layer like that within a transformer, or they could mean a full embedding model. Typically, this is going to be a BERT style large language model, but the definition of the word embeddings, as you'll notice when you read papers, literally depends on the context, which is a quite meta thing, as we'll see. Okay, let's zero in on some of the language here. Embedding representation. This is simply a vector, a list of numbers that corresponds to words. So it's a numerical representation of natural language that preserves relationships between words. Okay, so this word is about this far away from that word, and so on. When we talk about layers, these are within the transformer. These are simply mapping the input tokens to those dense vector representations that we need to do the attention calculations. Remember, the attention is all you need paper told us, similar to other sequence transduction models, we use learned embeddings to convert input tokens and output tokens to vectors. Now, there's one more thing here. There's an embedding model. And the embedding model is an LLM. I'm not calling it an LLM here because these labels like L and S are a bit ephemeral today. So I'm going to call it a language model. That's typically a BERT-style model that generates embedding representations. That's all it's doing. It's an embedding model. It models embeddings. It just generates them so that the input and the output kind of mean the same thing, but they're in different spaces. A good analogy here is kind of like complex numbers. You can sort of go to a complex number space and you might kind of mean the same thing, but you're in kind of a different space. And then you have to come back to make it really, really useful to you. All right, so embeddings. We already talked about sort of our little embedding quiz. Puppy is to dog as calf is to cow. We said, well, these are 2 dimensions. We want these 2 dimensions to be able to kind of expand to many, perhaps thousands of dimensions. And when we use thousands of dimensions, hard to visualize because we can only visualize 3, but we can start to zero in on these specific features in sort of a classic machine learning sense. These features that are going to be very, very helpful for downstream tasks. And we can use these vector representations to do math, like to do attention calculations and stuff. And, you know, this is one of the most iconic examples from the illustrated word2vec, same author as the illustrated transformer, really, really showing that, you know, dense vectors can really represent text quite well. Now, that was 2013. We'll get into that. Today, you know, OpenAI is embedding models. There's lots of embedding models. We'll talk about that as well. Here's a great way to think about these embedding vectors. 1 minute from Grant from 3 Blue 1 Brown here.
Consider the phrases American shrew mole, 1 mole of carbon dioxide, and take a biopsy of the mole. You and I know that the word mole has different meanings in each one of these, based on the context. But after the first step of a transformer, the one that breaks up the text and associates each token with a vector, the vector that's associated with mole would be the same in all 3 of these cases, because this initial token embedding is effectively a lookup table with no reference to the context. It's only in the next step of the transformer that the surrounding embeddings have the chance to pass information into this one. The picture you might have in mind is that there are multiple distinct directions in this embedding space, encoding the multiple distinct meanings of the word mole, and that a well-trained attention block calculates what you need to add to the generic embedding to move it to one of these more specific directions as a function of the context.
Okay, so that's a really interesting point here that we can sort of connect to attention, that we need to sort of think about what we might add to the embedding to make it go to where we would expect it to be based on the context. This is sort of like, okay, it's starting to make sense why we'd use these types of representations to do the attention calculation. Okay, so we take words, we turn them into numbers. Generally, we can think about the words as full words. We don't need to think about them as sort of tokens or subwords. Now, what also happens here later, and we'll talk about this a little bit today, is they're actually pooled together at the end. Because just like this, they're just independent words, but they're actually all connected. And we have encoded positional information already, but we need to sort of pool their understanding of what they've attended to together so that we're really looking at that sentence or sequence level. Typically, when we train these things, we'll have data that looks like this, like a person on a horse jumps over a broken down airplane, or a person is outdoors on a horse. Like we would expect these sentences to be kind of close in embedding space. And, you know, we would want the input, these words that would be used as input, and whatever the numbers are that are predicted to be semantically similar. They got to mean the same thing. That semantic similarity is a closeness in embedding space. So when we put either one of these things in, we're going to get roughly the same numbers. That is roughly the same position in embedding space. Okay. What we want to talk about is before we sort of go into embedding models, we want to talk about this idea of rope embeddings. Now, rotary positional embeddings, you'll notice instantly start to confuse the language we've learned already. Positional encoding recently has shown to be effective in the transformer, April 2021. Rope integrates positional information into transformer-based LLMs using this rotary position embedding. Wait, hold on. You're encoding positional information using an embedding? That's right, because encode and embed are, in some sense, kind of synonyms here. Now, what this gives us is it gives the flexibility of sequence length. That is to say, we can put super long sequences in to a rope embedding transformer. In fact, they're great for what are called long context LLMs. And in a long context LLM, we just ask a question, we just dump in, copy, paste all the context we can find. Boom, we send it to the chat model and we sort of get our answer. This is the long context approach. And what it does is it leverages the entirety of the context window. So you've probably noticed this. These keep getting bigger. The context window includes all input tokens and output tokens, as well as control tokens. Like, they're actually, in a transformer, there really is no in and out. Like, there is only context, which we kind of intuitively know already, right? And as we'll see, when we go to try to optimize context, we try to really optimize that context. We start to move into this space of RAG, but we'll sort of put a pin in that. Again, it includes all of this stuff. So when you look at something like Llama 3, 8K context window, when you look at something like GPT-4o, much larger, we've seen these context windows grow and grow and grow and grow and grow. No matter what the context size is, if you want more input, you get less output. If you want more output, you have to deal with less input. It's like a window. And it has a fixed size, like all windows. You can slide the stuff. And so what rope does is rope basically says, I'm going to allow you to put super long sequences in. And it's going to be okay because of this long-term decay property, which means that this multiplication, this inner product multiplication they're doing, will decay when the relative position between tokens increases. So like, if I have one word and it's super far away from another word, probably it's inherently less related, but it still is keeping track and attending to that super far away word. So, the authors just so eloquently write, simply rotate the affine transformed word embedding vector by amount of angle multiples of its position index. The sentence goes on to say, and thus interprets the intuition behind rotary position embedding. Okay, the word here is rotate and rotary that we want to pay attention to. This rotational positional encoding, aka embedding, is just a learned positional encoding, plug and play, that instead of the sine cosine representation we use for the transformer, we're going to use this one. Wiz is going to show us how this works. This is demo only, so feel free to just enjoy the show here, everybody. Let's see how rope embeddings look inside the transformer and how they get trained, just like any other positional encoding. Wiz, over to you.
All right. So yes, thanks, Greg. We'll clear up a little bit of the language. So we don't train rope. It's not a learned representation, but we absolutely do apply rope when we have our embeddings, which are learned. So in this notebook, first of all, you've probably seen this notebook before, but this time it's even differenter. So we're going to look at this diagram, and the first thing that should jump out to you is, hang on a second, where is the positional encoding layer, right? Like, I'm not seeing it. This is one of the advantages of something like rope. We don't have to have this extra layer. we're actually going to just apply the transformation as part of the attention mechanism. Thanks, rope. So we don't need that extra layer, but we do need the same thing we normally need, which is some embeddings, because we need something to apply rope to, and what we're going to apply rope to is those embeddings. And then we still do need to care about positional encoding. So we have our rope or rotary positional encoding layer available here. It's just a transform, so we don't have to basically like deep copy the vectors or the matrix that we're using. All we have to do is pass it in and then do some transformations. The big thing is that we have this rotate half idea. So because at the end of the day, what rope is going to do is it's going to create pairs of elements in our embedding dimension, right? So when we think about a sequence of embedding vectors, we think about like we have token 1, token 2, token 3, token 4, and each of those tokens has a vector representation. That might be, say, 10 elements long. What rope does is it pairs off those embedding vectors into embedding pairs. So for token 1, we'd have the pair of, the 0th element in the first element, and then the second element in the third element, and so on and so forth. And then we apply this transformation to those embeddings. So the way we could think about it extremely loosely, using very loose language, is we kind of twist the embedding dimensions or the embedding vector, and the amount we twist it is dependent on where it exists in a sequence. However, each time we step through to the next token in a sequence, we get this this multiplier, right, of how much we twist. And what the multiplier does, right, on this twisting action is it means that the resultant transformation of each embedding vector, I'm going to use the big math words here, is rotationally invariant. So rotationally invariant just means it looks the same if we're just looking at the rotation, right? So it doesn't each time we do the rotation of the first pair, no matter where we are on the sequence, right? It's going to look the same, just how many times we've rotated it. A very oversimplified way of thinking about it. The reason that's useful is that every single token in our sequence is going to have the same amount of relative twisting applied to it based on where it exists in the sequence. And how that's useful is it lets us really understand both these very short-term connections or very close connections, along with these very distant or very far connections. So you might say, well, how does it do that? Well, one part that I didn't talk about yet is as we move through the embedding vector, we rotate or we twist slower and slower. So the embedding vector, the pairs of embeddings that we rotate towards the beginning of the embedding vector are rotated very quickly, and the ones that are very far down the embedding vector are rotated very slowly. And so what that lets us do is it lets us both it's the classic metaphor, right? We're going to use it. It's like the hour hand, minute hand on a clock, right? We have the ability to understand both these long distance relationships as well as these very short distance relationships. And again, that rotationally invariant piece, all that means is, the angle between those two is going to be the same for any given pair in that sequence, no matter what section of the embeddings we're looking at. So what this means is that when we look at the first token in the sequence and the last token in the sequence, the amount that they're different is going to be the same across all sequences, assuming that we have that fixed context length. So all of that math, right, is just saying we're twisting the embedding vectors very carefully and cleverly so that no matter when we look at pairs of them, they always, the same distance always looks like the same amount of or same change in information. And someone asked a great question maybe it was at the beginning of week 2 in cohort questions, which is like, well, what about the magnitude of these embeddings and the positional encodings? You know, if I'm adding something to my embeddings, then aren't I changing its magnitude? And how do I live with that or deal with that? Rope helps us move away from that adding, right? It's just twisting now. So instead of having this change in magnitude, we can keep our magnitudes consistent, which is nice. How's it look in code? You know it's straightforward in code. So the big thing is we have a rotation matrix. This is just the matrix for each of the given positions. All that means is because we have to twist things at the start of the embedding sequence slower than the things at the end of the embedding sequence, then we need to handle that essentially. Then we have this rotate half. Again, because we're doing pairs, we're just rotating half. We have our forward pass. Very straightforwardly, all this is doing is doing some tensor management here, which is to say making sure things are the right shape. And then we do this complex multiplication, because technically every single every single item in our embedding matrix could be thought of as a coordinate. We think of these pairs as complex coordinates, which is why we use the term complex here. It's just the math version of complex, where it represents a complex number, and then this is the math straightforward. Okay, so now there's no layer though, right? This is just a process that happens. So we have to go all the way to our attention implementation in order to see where this happens. And we just scroll on down, and you can see here that we have apply rotary position embeddings. We just rope Q and R, and then we have a regular tension where we apply to Q and K some rope. That's all that's happening, right? This is a shortcut. We can just do it here because we don't need to do it at the start in this big batch process that's slow. We can instead do it here because it's just a transformation, right? There is no we don't have to keep track of all of the embeddings and then add stuff to them and concatenate, which is a side benefit of rope. It's less computationally complex, which we love hearing. But that's all we do. So we take our we take our Q, K, and V, just our Q and K, and then we do rope on it, which is a fun thing to say. And that's it. That's all we have to do, right? Very easy, very straightforward. Thanks, code. So what does it look like once we've used it, and why do we care? We're going to scroll some more in order to look at some graphs, because we love looking at graphs. No, it's not applied to V. You'll see here that we have this idea of how much we're rotating things depending on their position, but they're just multiples of each other, right? So this is the same if you're looking at it like hour hand on a clock or whatever, right? When we shift it up, it's the same. When we shift it over, it's the same, and on, right? Each of these pairs of vectors has the same angle. And then you'll notice here that we have this, depending on the actual position in the sequence, right? Our dimension pairs are being rotated either very quickly or very slowly. So we have this idea that we have our 0 and 1th dimension pair being rotated extremely fast, 4 radians, right? That's big rota. And then our 2nd and 3rd dimension pair being rotated much less. But as we move from 0 to 1 to 2 to 3 to 4, you'll notice though that these look very much just like there's some kind of scalar multiple, right? Because that's all it is. We have the first position, we're going to do 1 radian for our first pair in our embedding sequence, and 0.1 radians for our second pair, and then 0.01, et cetera, et cetera. And then if we look at position 4, right, it's just 4x what we did here. And this is that thing that lets us say no matter how we're looking between these sequences, we have the same information captured by that rotation that lets us understand that very long distance and short distance relationship. And then you can see here how it manifests in our actual attention. which is this is going to be our Q and K, and this is our attention score. Basically, everything is the same in regular attention with no position information imparted. And then here we have that the attention scores look different depending on where they are in the sequence. Everybody hopefully understands we need to impart that information. Rope just does it in this way. I think the most useful thing to understand here is that, you know, these are multiples of each other. There is no secret sauce here. The further we go down the sequence, the higher the multiple is. And you might think to yourself, well, so okay, if it's rotationally invariant, how do we know the long distance relationship? Well, because we have actual values, right? So even though they're rotationally different, the actual value in each of these dimension is going to be different. And so there we have the ability to see long distance relationships along with short distance relationships. That's rope. That's all it is. It's basically just doing what we did with the sinusoidal relative positional coding and juicing it up to the next level. And then as for why this generalizes well, which is always the question, right? Why does this matter, right? Greg was saying it's very useful for long distance sequences, and it is. But how does this, how do we get a benefit from this when we train short sequences? How does rope help us understand longer sequences? Well, because the model is still learning this this relationship between those tokens in those positions, and so it's easier to extrapolate that out, right? The model has already learned that there exists this relationship, and because of that rotational invariance, the model doesn't have to learn a new thing for when there's a sequence that's extremely long compared to what it was trained on, because again, that relative position is always going to have the same relationship thanks to that rotational invariance. The big story here is the model doesn't have to learn a new thing for longer sequences. It's just using the same thing. And so we still want to fine tune on longer sequences, but we certainly don't have to in order to get some benefit thanks to rope learning the kind of core idea of what does distance mean to the model. And that's rope. It's really cool. It's really easy to implement. It's used in basically every modern model from starting from like Llama 2, Llama 3, 3.1, all of them are using rope. This is how companies like Gradient took Llama with its 16K context or 4K context, whatever it was, and then gave us a 1 million context length model, right? All in the back of rope. Yes, Ben, that is one of the key benefits of rope, is that it helps the model generalize from short to long. We still want to train, but yes, that is one of the benefits we get from rope, along with a handful of others. And with that, we'll go back to Greg.
All right, yeah, so that's rope, and we had to tell you about it because it is the thing that gets used today, and it is fixed. Let's get that right, myself included. Rope is a fixed encoding representation approach, whereas the learned embedding approach, the learned positional, the positional encoding last time also was fixed as well. Okay, so the positional encoding fixed, learned embedding representations. Speaking of learning embedding representations, we're going to stick with the earliest and most iconic example. We want to go into this with you guys, and this is sort of the crux of today, really grokking embeddings in general, and then we're going to extend this. There's two types of embedding models. And for those of you that studied classic NLP, this will sound familiar. There's context and no context. And, that makes sense based on what we've discussed so far. If you have a word and it's just by itself, that's just a vector. But we have to sort of tell you where it is related to other words and other vectors. These no context approaches are probably where you started learning natural language processing. Remember, like bag of words, right? Count vectorizer. And you were like really sweet if you did like the TF-IDF, right? Back in the day. Well, what are we talking about? We're talking about, well, no context, not as good as yes context, right? Not as good as putting the right stuff in context. The yes context things are things like word2vec. This is, we could talk about the continuous bag of words approach or the skipgram. You guys, as you dig into the notebook, you'll notice some of these things and they might sort of bring you back. If you've never studied this, it'll be sort of an interesting thing to look at. You may recognize some of these other names from back in the day, but we could also think about our good friend, the multi-layer perceptron, the feed-forward neural network. This also embeds context, right? With the hidden layer. We're starting to bring this all together a little bit. Now, the earliest example here is word2vec. As we saw, king minus man plus woman is about queen. That is not quite salacious enough. How about, what do we get if we do Hitler plus Italy minus Germany? What do you guys think? Let's see what Grant has to show.
What is Hitler plus Italy minus Germany? This came up in a full video that I did dissecting what happens inside large language models. You see, when tools like ChatGPT process text, the first thing they do is subdivide it into little pieces, and they associate each piece with a large vector, some long list of numbers. This is called an embedding of that piece of text, and it's helpful to imagine these embedding vectors as directions in some very high-dimensional space, even if we struggle to concretely visualize anything more than 3 dimensions. Models that learn to embed words as vectors like this often encode meaning into the directions of this high-dimensional space. If you take the difference between the embeddings of man and woman, and you add that to the embedding of uncle, you get a vector very close to the embedding of aunt. If you take the embedding of Italy minus Germany, and you add it to the embedding of Hitler, you get something very close to the embedding of Mussolini. It's as if the model learned to associate some directions in this high-dimensional space with Italianness, and others with World War II Axis leaders.
All right, so pretty cool. Now, this correlation that we're doing, this encoding of vector representation into this embedding space, right? It's just similarity all the way down. It's basically typically cosine similarity that we're using. We use this in a lot of places. We've used it historically in natural language processing, k-nearest neighbors type algorithms. The real stuff that's at the core of what we build today really isn't all that different. And you'll notice the paper that he pointed out in the video is the original paper from 2013, the word2vec paper, where they basically said we got 2 novel model architectures, continuous vector representations of words from very large data sets. Less than a day to learn high quality word vectors from a 1.6 billion words data set. We're going to create our own data set today. We're going to take Gladiator 2 and Wicked information down from their Wikipedia pages and build you a word2vec embedding model from scratch. Or rather, you're going to build a word2vec embedding model from scratch. Wiz, show us how it's done.
Oh, yeah. Okay, so embeddings. What do they mean? The first thing we're going to look at is just what's in the notebook. So this notebook is going to have a number of things for you to do, depending on the version you select. You're going to at least have these questions, activities. Please make sure you do all of those. In the breakout room, you'll be working through this first section, which contains at least these 4 total things to do. So make sure you do that with your breakout room. It's very straightforward in the first one. The idea of embeddings is it just comes from necessity, right? We must have embeddings because the model doesn't actually understand words. Much less does the model understand meanings of words, right? Embeddings are what let us have meanings of words, basically. That's it. So when we look at the first thing we're going to do in the workbook here, it's going to be training word2vec from scratch. Word2vec it's going to blow your mind a little bit to learn. It's about converting words to vectors, right? So that's the whole idea of word2vec. This is the original original is probably too strict of a word, but this is one of the original ways that we had to convert our words or our natural language into meaningful tokens or vectors of information, which we could do cool math on. The big thing is, yes, absolutely, like Greg suggested, like Grant walked us through, we have this idea that we can do math with these vectors, and so we can do math with words in the same way we would, right? Which is pretty fun. Okay, so first things first, we're going to install some dependencies. I'm going to recommend that after you install the dependencies, you go to your runtime in Colab, and then you click restart session, which is available here if you're in an active runtime. This is going to help. This is going to help you understand if there's any issues with, naming conflicts as we move to the notebook. Data sets is sometimes a little bit troublesome when we're using these old libraries. Okay, then we have to do some data collection. The data collection is pretty straightforward. All it is searching Wikipedia for articles about the thing and then downloading that. As you can see, we are just pulling the actual thing from the Wikipedia page. We're loading the Wikipedia page. We're using this weird library called LangChain, which we will absolutely spend no time on at all, other than it is useful because it has this Wikipedia loader. So it's just a fancy Wikipedia loader. Very cool. Okay. But you should look more into LangChain if you're interested. We're going to get both from Wicked, the 2024 film, and Gladiator 2. That's right. There was a second Gladiator. Very cool. The next thing we're going to do with this data, because when we look at this data, right? So like, let's go to the Wicked 2024 Wikipedia page for a moment, right? First of all, you know that they're always looking for money, so donate to support Wikipedia if you want to. Second of all, you'll notice that this is like, there's a lot of stuff going on here, right? There's paragraphs going on here. There's capitalization going on here. There's weird punctuation. There's commas everywhere. This is insane. So what we want to do is we want to normalize our text. And this is necessary in something like these earlier bag of words, right? Based approaches, or these skip-gram based approaches, because what we want to do is we want to kind of we want this wicked to be the same as that wicked to be the same as the word wicked, right? We want to have one representation of this word. We don't want to have like capital wicked and lowercase wicked. Peter Dinklage is in it. Great movie. Okay, so the way we do data pre-processing is, or text normalization, is we remove special characters. Then we remove stop words. This is an interesting one, right? Because both of the skip-gram and continuous bag of words approaches, more on that in a second, depend on like word frequencies and where the word appears and what documents the word appears in, right? There are some words that are like in everything. For instance, the word the word a, these words appear in everything. And so they're kind of useless to us. We don't care about the meaning of the word a or the. That's not the part of the word that has important semantic meaning. We're going to move links, and we're going to convert to lowercase, and we're going to strip all the white space. Very cool. To do this, we're going to use regex and spacey. So we will use as well NLTK. NLTK is, if you're from the old school NLP world, much love to NLTK. It got us through some dark times, but unfortunately now it's kind of, we're not using it as much. And then let's look at what these stop words are. Again, we have this I, me, my, myself, we, ours, ourselves, you, your, all of these words which are not information carrying is how we're going to define them. Okay, so we use a big ol' helper function that pre-processes our text. It does the things we want, like remove links, remove special characters, tokenize the text, make lowercase, and remove stop words. When we say this word tokenize the text, we mean convert it from some long string or sentence representation to a short tokeny representation. The token representation in this case is going to be words, right? That makes sense because it's word to vec. So our base tokens are going to be words. This is the idea. When we look at transformers and tokenization strategies, we might go below the word. We might go subword, but for word to vec, we're going to keep it at the word level. Anyway, this does Python that does all that. And then we can give it a sentence, and we can have, original sentence, and then we go to the Wicked titled On-Screen Wicked, part American musical fantasy film directed John C. Very cool. Okay. Then we're going to create a sentence tokenization helper function, which is basically just going to take our full corpus of text and then turn it into sentences and then apply that pre-processing or normalization to each sentence. So now we're going to have a list of lists where the parent list is going to be sentences, and then each individual list in that list is going to be, of course, words in the sentence. Very cool. Okay. Then we're ready to just lump these all together in a big old list. And so that's exactly what we do. We have a question here. Why is normalization tokenization necessary to train a word-to-vec embedding model? And then we have a discussion question. When creating training data for large language models, do we still care about any of this, right? So what is your understanding? What have you seen? And what arguments do you have for and against as we have these bigger and bigger models? Okay, and then we have the actual training. We're going to use GenSim. GenSim is an old school classic thing. We also have an aside on skipgram and continuous bag of words. We're going to be using skipgram because it's better for this use case. It's slower, but it's better for the use case. That's why we're using skipgram. But SIBO is pretty good if if you were dealing with a different kind of data, or you had such a large volume of data that computationally skipgram became less effective for you. If you want to read more about them, that's that. We are just going to use skipgram is the idea. Then we get into our first activity, which is set some appropriate hyperparameters. So you can play with these, change them, create a new vector size, shrink the vector size. One thing to think about when we're using phrases like vector size, or we're thinking about embedding vectors, right? So we had that example in the last class where Greg showed us a 2D axis, right? And the axis had like basically what we thought of as like age or size, and then what we thought as like which animal, right? So we had like cow to calf, and then we had dog to puppy, right? Now that's two axes that we can describe. So as we increase the number of axes in our embedding vectors, right, we can describe more relationships, right? So though it's not literally true to say this, it's a good conceptual understanding to think of each of those axes as a comparison axis, right? Something that we can think about this thing existing along. So like between like a white and black cow and a brown cow, we could have like color as one of the axes, right? Is it spotted, or is it not patterned, right? That could be an axis. And so that the idea of these vector sizes loosely relates to that understanding. Okay, so once we set up our hyperparameters and you define what they are using the documentation is here, then we train the model. Because our corpus is tiny and computers are fast now, this happens instantly. So it takes absolutely no time to train this at all. And then we get this machine that will let us type in words that were in our corpus. Very big caveat, right? Words that were in our corpus. There is absolutely no reaching outside of our corpus for this method. It only knows words that it was trained on, right? We can now convert our words into big lists of numbers, and then we can do the thing, right? So we can say, what is the most similar vectors to the vector Elphaba? Elphaba is the Wicked Witch of the West. That's just her name. Who is the most, or what is the most similar vectors to Maximus? Maximus, a gladiator, right? And we get Commodus, Sun, Emperor. That's because you can kind of read these in order to determine what's going on with Maximus. If you want to save yourself a quick Google. Now we can do the thing. right? The vector math. We can do the Galinda, who is the good witch, right? She's the one in the bubble, wears sparkly crown, very cool. And then we can subtract the idea of the vector that represents good from her. And what are we left with? We're left with Elphaba, the wicked witch, right? So we take the good witch, we subtract good, and we're left with the bad witch or the wicked witch. I mean, that's yay, we did the thing, right? So this is just from 2 Wikipedia pages. You can imagine if we had 1.6 billion words as opposed to a couple 100,000. That's it. That's all we have to do for word to vec, right? The training is entirely covered in this word to vec thing. That's it. That's all it does. And what's happening under the hood, we're taking words, we're taking other words, we're seeing if they should be close. Their closeness is determined by literally being in the same sentence as each other. And then we update the weights accordingly. We can also do a sweet little visualization. Shout out to Alan for thinking this is a good idea. The visualization shows us things like Glinda is close to Glinda because they're the same guy, right? There you go. Makes sense. Morrible is close to Madame because the character's name is Madame Morrible. Who knew? We have Fiero, we have Nessa, these are characters, and then we have Shiz, which is the name of the university, right? So Shiz and university mean the same thing. They refer to the university as Shiz. So those words are pretty much interchangeable in the story, and so we see them being extremely close as a vector representation. That's it. That's how it works, right? This is the thing that we're trying to do. This has been T-sneed all the way down to 2 dimensions. So obviously, we're losing, we're losing information here, but it's close enough. Tells the story, and that's that. So with that, I'll pass you guys back to Greg, who will move us into breakout rooms.
Yes, I want to just note that we are at 55 after the hour, so we're going to take a breakout room, a solid one, and then we'll take a quick break. This is sort of the main crux of the session, just as we did last time. After we focus on the fundamentals in this one, we'll sort of rapidly scale up to the state of the art to show you guys exactly what the embedding models that you're going to be pulling off the shelves as you start building applications for production, what those look like and how it connects to what we've talked about so far. So enjoy the Word to Vec with the latest and greatest movies out in theaters now. And we're going to open up breakout rooms for 20 minutes. Have some fun with your breakout rooms. And peer supporters, you know what to do. And we are back from the quick break. So we've got to sort of ramp into where we're at today with embeddings. I can just say that now, right? Embeddings. This is the massive text embedding benchmark we're going to look at real quick. Now, one question is, which embedding model should I actually use? Should I train my own? What's the deal? Well, it turns out there's really good embedding models out there. And this embedding benchmark was created in October 2022, basically saying that no text embedding model is basically dominant across all things you might use embedding models for. Embedding representations are incredibly general, and you can use them to solve all sorts of different tasks. So what we end up with is this sort of, we have to choose. Now, you can look at things like how many parameters are in the embedding model, how much memory does it use, what are the metrics and the benchmarks and the performance that this thing has achieved. And then generally you just try to, okay, pick the smallest one. And you can look at this on Hugging Face. They've got a great sort of embedding benchmark leaderboard, and there's all sorts of stuff. We go into this in more detail in the other class, but there's just a lot of different things you can do with embedding models. And you can see that there's a leader on the leaderboard. So that's pretty cool. And one of the other things you can do is, you can sort of follow some of these best practices that we generally will outline. And really, if you follow our best practices and you like can't find one, then you really haven't thought through your problem well enough to be able to select one. So I would recommend going back and doing the product development work to be able to select a better embedding model. But the other thing that you can do is you can just basically be a super Chad and just pick the biggest freaking one and the one that's the leader. And today it's the NV Embed V2. You see it's there on the leaderboard right now, sort of the best in general. Now, fun fact that we have no time to dig into today. This is tending towards a more GPT style of embedding model, which is something that's quite new. Just a trailhead for you guys to keep track of. To date, pretty much embedding models have been more of the BERT variety, as we'll see. And what they've been good at doing is they've been good at doing one of the most popular things we do in programming, period, but certainly one of the most popular things in generative AI, retrieval. This is something we want to do really well, because when we retrieve the right context and we put it in context, then we can do amazing things with these AI tools. So, we'll end up seeing at the state of the art things that actually use a simple retriever, just a sort of bag of words style, if you'd like, that are sort of looking for almost exact match or fuzzy match things. And then we'll do sort of a more semantic retrieval. So if you think about an example like this, error code TS999, the embedding model might come back and it might get error codes, and it might find stuff in your documents that is related to error codes. Whereas the best match 25 might be much more able to find something like TS99 in particular. So we end up with these sort of ensemble approaches where we're doing like an old school keyword search. Think of what Google is doing, what they've been doing for 20 years. And then what the other piece is this dense vector retrieval, which is where embedding models come in. And this is where sentence transformers come in. Sentence transformers. So we're using sentence embedding representations. So we're comparing sentences to other sentences. And sentence transformers is also known as sentence BERT. Sentence BERT, of course, should start to make some sense to you guys, because underlying this is a BERT style model. The BERT style model takes as input sentences and outputs embedding representations. How great! That's exactly what we're looking for. We can actually use this to output embeddings directly. We can use it to do similarity searches to words that we have already that we're looking for similar sentences, or we can even return like the most similar things in the space. This is something that's quite important when we go to start optimizing context. And this retrieval process of dense vector retrieval is something we'll see over and over again. In fact, this is the foundation of RAG, or retrieval augmented generation. This is something we go into great depth in elsewhere. I just want to tell you that we do this to try to avoid hallucinations in LLMs by retrieving reference material from our docs, adding that reference material in context, and then doing our generation. So we do this retrieval, and then we do in-context learning. We ask a question, we send it to the embedding model, we get that embedding representation. We use a sentence transformers library or equivalent to sort of look through our data that we've already embedded and stored as vectors in a vector store. And we try to find what are the sentences or the chunks of data that are most like my question. I'm going to set up a prompt template that says, use the context and don't lie to me. Don't lie to me, I'm sorry. And this retrieval process is what we're using the embedding model for, to put the right stuff in context so we can actually do RAG or do augmentation of the prompt through retrieval so we can then do the final generation. So this sort of asking of a question, searching a vector database for stuff that's similar to the question, and returning the stuff, this is where we actually use these embedding models, where we compare sentences to other sentences, where we compare chunks to other chunks, where we compare our source question to context that we want to retrieve. And it's here that we end up fine-tuning these embedding models to help us out to be more like our data. Another way we can describe this is to domain adapt these embedding models to our domain. As we'll talk about in great detail in a future session, fine-tuning is about teaching the LLM exactly how to act, what input, what output, or teaching the embedding model how to adapt to our words, right? And of course, an embedding model is just an LLM. It's just an attention-driven transformer of the BERT style. Remember, what is BERT? It's the encoder. It encodes the information in the sentence, in my question. It allows me to really grok and understand that input. It's really good at things like question answering. And so when we go and we try to increase performance of a system like a RAG application, one of the easiest ways to do that is by fine-tuning embeddings. And the way that we do that is we collect question context pairs, and we use something called synthetic data generation to basically take our data and say, use that data to create question context pairs, and then we fine-tune our embedding model. So we take the stuff from our documents, we chunk it up, we run it through the embedding model, we put it in a vector store. Then we take the stuff we put in that vector store, and then we use this SDG or synthetic data generation to basically say, these are my chunks. Now I'm going to feed it into another LLM, a GPT style LLM, where I'm going to say, generate questions based on these chunks. And then I'm going to take that pipeline and I'm going to say, now take those questions and take the corresponding context and use those to train the embedding model. So what we'll do is we'll basically take an embedding model off the shelf, one that's already been trained in general, and we'll use a specific kind of loss called the multiple negatives ranking loss. What we want is we want positive pairs, that is things that are similar, to be close in the space. And we want negative pairs that are also synthetically generated to be further away in the space. We know this is a lot, and this is something we cover in multiple weeks in the AI Engineering Bootcamp, but this is how stuff's done today, and it's important context for you to think about when you think about embedding models. With that, we're going to go over to Wiz to show us exactly how easy it can be to fine-tune, and we're going to focus on the ease and the intuition of fine-tuning today, where we'll dig into some of the details of fine-tuning in a future session. Wiz, over to you.
Oh yeah, okay. This is the good stuff. So we're we were in 2000 before 2018 just a second ago. Now all of a sudden we've traveled the speed of light and we are at 2023 or something like that. Depending on because we're using a BGE small. Okay, so first things first, we're going to be using something called a sentence transformer. Exactly like Greg said, it is a transformer. We typically apply it to sentences. That's it. There was a great question in the chat that we'll just spend a second on here. We never actually look at the sentence as in, we never directly embed a sentence with sentence transformers. What we do instead, as we'll see in a second, is we embed each token in a sentence, and then we apply some pooling operation to consider the pooled representation as the sentence's representation. And then we're going to train on that objective. So that's how our model is going to be good at knowing about sentences. So first things first, we just do some imports. We have to load this model. We're going to get into what all is happening here in just a bit. For right now, just know it's really easy to load models. That's it. Okay. Then we look at our model and we can see we've got a couple things, right? So this is a transformer model. It's a BERT model. So this is the encoder only. So it's with the decoder chopped right off. We just encode. We have many stacks of encoders. And then we have our pooling. Now our pooling has a couple things we want to think about. Word embedding dimension. So that's the dimension of each word. Each word has an embedding dimension of 384. This is because we're using a tokenization strategy whereby we convert English words into embedding vectors. You'll also notice that we're doing this pooling mode CLS token equals true. Back in the day, we used to think of a sentence as just the CLS token. So in order to determine what a sentence's embedded representation was, we just looked at the last token, the CLS token. Okay. Now this research, sentence transformers, which you can read in the paper, was like, actually, we should look at the whole thing and then we should do some pooling. Okay. So, and then we have a bunch of other things about pooling, and then we have our normalization. Okay, cool. So and then we have this do lowercase. So there's some normalization happening, right? There's some of those things we talked about from earlier are happening with this particular model. So what does pooling mean? Well, basically, every word has an embedding dimension of 384. And what we do is we look at the average of every single one of those 384 dimensions across each token in our sequence. So let's just shrink the numbers down a little bit to make it make sense. Imagine we had a sequence that was 5 words, right? The cat is almost here, okay? So I had to think of a sentence on the fly, my bad. So the cat is almost here. We have 5 words. So we're gonna get 5 different word embeddings. Let's just imagine, for the sake of simplicity, that we only have 2 dimensions in our embedding dimension, right? What we're gonna do is we're gonna look at the average for the cat is almost here in the first dimension, and that's gonna be our pooled representation, and then we'll repeat that for the second dimension. So we'll just take an average across each of those dimensions for each token in the sequence. So we wind up with one thing that represents the whole sequence. That's what that pooling is doing, right? So we could do this with word to vec. It would be a bad idea, but we could do it, right? And this is the idea with the sentence transformer. Okay, so that's all on this pooling thing. How under the hood we actually do token-wise embeddings, and then we just do math to figure out what the full representation is of the sentence. And then we're going to do some data loading. We're not going to really talk about the data here. Suffice to say that we have QA pairs, which is question answer pairs. The expectation is that the questions are semantically similar to the answers. That's it. That's an assumption we're making. In this case, we made that to be true because we synthetically generated this data, which we'll talk about, or which we do talk about in much more detail in a different course. We're going to be using this multiple negatives ranking loss. Boy, that's a mouthful. What does it mean? So we're going to do what's called contrastive training here, which means that we are going to use contrasting pairs, right? If you know the word contrasting just from normal English, it's the same thing. We're gonna by showing it these 2 things that are very different, we're gonna be able to say, okay, this is very close to this thing we want it to be close to, and it's very different from all these things we don't want to be close to. This multiple negatives language is just saying for every pair we have in our data set. So let's say you have 10 items in our data set, right? We know that the first question answer pair should be very closely related. And the assumption is that every other answer should not be close, right, to the first question. So rows 2 through 10 shouldn't be close to row 1's question. And so what we have is we have 1 positive and then many negatives. And the reason we choose 10 here is because this is applied per batch. So we literally have batch size of 10, which means that we actually have 1 negative or 1 positive example, and then we have 9 negative examples. right? So for every time we want to learn what a embedding is, we have 1 that it should be close to and 9 that it should be not close to. And what I'm saying close to, right, which is very ambiguous language, what I mean is that the output of the model, which is going to be, again, that pooled representation, or one embedding vector that is pooled to represent an entire sequence, should have a low cosine similarity compared to our source vector for negative options, and it should have a cosine similarity close to 1 for the related sentence. So that's it, right? So that's what this loss is at all. Now, again, we just do some transformation for our data to make it look good for our model. And then we do the train bit. And this is all we're going to talk about, the train bit. We do the train. In this case, you're going to be prompted for a wand B key. You can straight up just click the provided link, and it will tell you how to do that. But that's what we're going to do. We're going to use .fit here, which is another word for just .train. So we're going to fit the model. And again, what it's going to do is it's going to take the data and our loss and use that as its objective. So we're going to try to make the loss get low. That's all we're doing. And what is the loss in this case? Well, at the end of the day, it's just that cosine similarity. The idea being that sentences that should be close together should have high or cosine similarity close to 1, and sentences that are not related should not have cosine similarities close to 1. And we're just going to measure and see if that's true or not every time we do an iteration. And then we're going to use, we'll talk more about training in the future. What we get is this output, which reports to us a bunch of different things, which is cool. And then we're going to go ahead and evaluate our embedding model. We're going to evaluate the embedding model on a number of metrics. And these metrics are going to have these very fun little @1, @3, @5, @10. What these metrics mean is basically, what is this metric given we look at the top K examples, right? So accuracy at 1 is how often do we retrieve the expected thing if we just return 1 document, whereas accuracy at 3 is saying, what if we return the top 3 closest documents, right? So our training set remembers questions and answers. So this is saying, how often do we return the correct answer, right, for our given question if we just use the most related answer versus we use the top 3 most related answers versus top 5 versus top 10. We also have these other more fun metrics, which you don't have to worry about too much. But the idea is that, again, they work at 10 or top K of 10. Top K is something that you're going to become very familiar with if you enter into the world of RAG. But for today, all it means is it's the top K documents or top K answers, given that our data set is specifically questions and answers. So we do the evaluation using our evaluation helper function. Your task is to describe what the heck the evaluator evaluate function is doing. You can look at the reference to documentation to see exactly what's happening. And then we will look at the final results, and we'll see that the model that we did not fine-tune has lower across the board accuracy, precision, recall, etc. So basically, our model that we fine-tuned got better at the task than the model that we didn't fine-tune. Now, what does that mean under the hood, right? It means that through showing many examples to the model, we made it so that the embeddings that we wanted to be closer together became closer together, right? So we wanted the model to think that, say, in this scenario, right, I always use an example from tennis, right? With the word love in typical English means, some affectionate feeling, etc. And the word love in tennis means 0, right? I've been told it's from the French word for egg, which is l'œuf. And if you say that, it sounds like love. There you go. Okay, so you learned something about tennis too. But the idea is that we have this we have this idea that we want to change the meaning of the word love. So we have to move it to a different place in that embedding space. And that's what that training's doing. With that, though, I'm going to pass you guys back to Greg, who will get us into this final breakout room where you'll be able to work through the code, answer the questions, and complete the activity.
Yes, thank you, Wiz. So what we're going to do is we're going to get back into breakout rooms now. And we've got a few questions to discuss the fine-tuning aspect here. Please do dig into any things you've found interesting. I can tell you for sure that as we get more and more towards the state of the art, the breakout room leads, the peer supporters, they are ever more comfortable in that space. So bring your best, and they've got some questions for you teed up already. We're going to see you back to close out class in just under 15 minutes. So try to make the most of your time together before we all break for giving thanks this week. All right, guys, we'll see you back soon to close out class. So we hope you had a good time in breakout rooms, and I'm highly cognizant of the time, so I'm going to steal just a couple of minutes from you before we head into the holiday break. I hope that's okay on a short week, because we covered a lot today. And one of the things that we learned is that the long context approach, just putting all of the stuff we want in context, leverages our friend rope under the hood of the transformer, the GPT style, the LLM. Whereas when we use an approach that is more akin to RAG, when we see something that looks more like a RAG system, we're not using a long context LLM here, although generally the models we pull off the shelf, Llama 3.1, they are long context LLMs. We're focusing here today on this embedding model and this retrieval process. We might pick one from the massive text embedding benchmark. We might use them using sentence transformers, also known as SBERT, at least when it was initially created. And we might do some fine tuning on that. And of course, we met our friend Word2Vec, the oldest OG in the game. Not going to be something that you put into production, but super fun, and really great to learn. And, one of the great places to really start dialing in your understanding. Rope is something that we want to understand. Word2Vec is something we want to understand. And it really is sort of the basis for a lot of the stuff that we end up doing when we can sort of look at this holistically, this first 3 sessions. We have one more session on next token prediction, where we'll really focus in on what happens at the end of the transformer, in the linear and the softmax layers, how we can put guardrails on our outputs, what are some of the state-of-the-art things like speculative decoding. We'll go deeper into decoding, whereas today we went deeper into encoding.